Dr. Mohan. In order to record his talk, maybe I'd like to introduce again. Okay, so Dr. Mohan is currently a distinguished visiting professor at Tsinghua University in China.
Is it being recorded already?
Yeah.
Yeah.
Because yesterday we forgot to turn on the recording when you were doing the introduction.
제가 메일로 좀 다시 전해드리겠다.
Okay.
I
A visiting researcher at Google, a member of the inaugural board member of governors of the University of Kerala, and an advisor of the Kerala Blockchain Academy (KBA) and the Tamil Nadu e-governance agency (TNEGA) in India. He retired in June 2020 from being an IBM fellow at the IBM Almada Research Center in Silicon Valley. So he was an IBM researcher for 38.5 years in the database, blockchain, and AI and related fields, impacting numerous IBM and non-IBM products. And the research and the academic community and standards, especially with his invention of the well-known Aries family of the database locking and recovery algorithms, and also the presumed abort distributed commit protocol. And he has been an IBM fellow from 1997 to 2020, and he is currently ACM and IEEE fellow. And also he has served as IBM China chief scientist, in addition to this, chief scientist, India. Okay. He has received a very prestigious award, including ACM Sigmod Edgar F. Card Innovation Award, the VLDB 10-year Best Paper Award, and numerous IBM awards. Also, he was elected to the United States and the India National Academy of Engineering and named the IBM Master of Inventor in 1997. Okay, so today he will talk about the cloud database. Okay, so please join me to welcome Dr. Mohan. Thank you.
So, am I good? I'm going to stand here and talk. No call a microphone, or I have to hold this one.
Yeah,
this one. Okay, thank
it.
you.
Yep.
Thanks a lot, Bukshin. We are just getting this. Sorry, we got delayed coming back. Let's see. Why is it not letting go? I'm trying to eject the USB drive. Oh, let's try. Let's hope that it wrote it into it. Did you find it or no?
Okay.
Oh, okay. Right. Thank you. Oh, you're checking the remote. Sometimes you have to click on it. Huh? Ah, okay. Thank you. Thank you very much. Thanks a lot, Bukshin, for the kind introduction and the invitation to come here and give me the opportunity to talk twice. Yesterday's talk was much more on a career path and all that, and do's and don'ts and such things, while using my own career as an example of somebody who has done a bunch of things, not all of which were successful in terms of having impact on the world the way I would have liked it to be. This presentation, on the other hand, is a lot more technical presentation, not career kind of stuff. And I've given it in a bunch of places, but I keep modifying the presentation as time goes on, adding more discussions about various systems and so on. So if you go and look at my this URL, whose QR code is this, that's a spreadsheet which has links to lots of presentations, including AI and blockchain and query processing and optimization and so on and so on. So it's a great resource if only people would take the trouble to go look there and follow the links from there. And that one is my homepage, which is in that Digital University Kerala. And that has links to my social media accounts and my email and such. And that also has a lot more information than this one in terms of my papers, patents, and various talks I've given across the globe. You'll even see Korea mentioned there because I came first time in 1991 to Korea. I try to make it very comprehensive in terms of links to all my papers and such over the decades. This presentation itself, this version of it, I haven't yet posted, unlike yesterday where before my talk I posted it and included the link in the presentation. I'll do it later today. And it will show up anyway over here. So this is a place, a go-to place for you to get access to my material easily. So I gave it as a keynote in a workshop attached to the ICDE conference back in April, I think. That conference was to have been held in Kuala Lumpur, but in the end it became all virtual. Also keep in mind that with most of my presentations, if you see it in the way you are seeing it now, which is the slideshow mode, you will see only a subset of the slides. There are other slides within the presentation which are hidden, which depending on the particular presentation might cover more systems or certain aspects that I felt I won't have the time to cover and so on. So I highly recommend that you go look at the slides in the other mode also, the edit mode, which is when, that's why you'll notice this went to, for the second slide is number 3, because there's a hidden slide in between. So there's a lot of material here. Is there a way to shut that thing? Yeah, I think I can do it. Let me. Okay. Yeah. Okay, if I want to go back. Yeah. So I stole, images from various places and things like that. And for not all of them, I've given appropriate credit. It's a thing in evolution. So when I did a seminar course last year, first half in NUS, I covered some of the systems that I'm going to talk about. And so I recommend that you go look at the seminar courses reading list, where I even have the abstracts of some of these papers. And as I said at the beginning, I'll keep evolving it. So if you keep looking at my social media accounts, both Facebook and LinkedIn, but sometimes Twitter, I'll post more links to more recent versions of these things as they evolve. So I'm going to discuss analyst view of the past and future, meaning, what they are predicting will be the market share and all that, both in the on-prem database market as well as cloud database market. I'll give a brief introduction to the cloud environment, both the overall big picture view of the cloud and then more specifically for database stuff. And then I'll talk about some of the expectations that people have that are different in the cloud environment compared to the on-prem environment, where you will have a lot of well trained or knowledgeable database administrators and systems admins who will be dealing with your installation of the DBMS and when to take backups, when to do reorg and all sorts of stuff like that. And because they are sophisticated people, if your system is hard to use, a lot of times they'll put up with it because they are not domain people who are not that much knowledgeable about systems and such. And whereas in the cloud environment, these things have to be a lot more self-managing and things like that. So that's where applications of AI and all that comes in. And then I'll get into discussion of some systems. I won't have the time to cover all of them. So if you look at this picture, this is from Gartner's estimate of what they felt were the revenues in the last 5 years. And also they categorize it as the cloud, the blue part, versus the yellow part, which is the on-prem non-cloud revenue. So as you can see clearly, the trend more and more is for bigger and bigger fraction of the overall revenue to come from the cloud environment. And in terms of the ranking of the different vendors, I'm very sad to see the company where I spent 38.5 years now sitting in the 5th position. Even Google has gone ahead of IBM. And interestingly enough, if you look at this picture, you know, the green colored ones have moved up. And then the, I don't know what color this is, beige or whatever, that colored ones have come down. So between 1 year and the following year, like 2020 and 2021, Oracle has gone down 1 level, and they had already gone down 1 level from the top position between 2019 and 2020. Whereas Google has gone up, AWS has gone up from 3rd to 2nd position. So the reigning king is now Microsoft. Okay. As you can tell, here it says the total market last year was 64.6. But if you look at the Gartner one, it says, well, yeah, it says 80 billion. So these analysts don't always have matching numbers because exactly how they count the revenue and all that is all highly subjective and things like that. So don't get too carried away by the absolute numbers. It's a better thing to look at the percentages and relative ranking and such things. But interestingly enough, they have said the overall revenue, according to Gartner, increased by 22% between 2020 and 2021. And so if you look at it this way, they're saying 64.6 and on-prem is 55% and cloud is a bit less, 44.3. So at least in the trends way, both are matching. That cloud is not yet the majority fraction, but it's getting there. And then if you look at the next, and there are more details here, right? Alibaba Group, which is close to Google, because the other picture didn't show you those things because it had only the top 5 guys, whereas here in the breakdown is more detailed. It even has SAP, for instance. Okay, I don't think SAP was ever in the top. No, it was the number 5. Oh, wow. For 4 years, it was number 5 and then it disappeared. Right. So this is now a projection. It's a forecast going forward for the next 5 years, what IDC thinks will be the overall market and the split between cloud and non-cloud. Look at this. It's now going to be a huge fraction by the time 2026 rolls around. Exactly whether this actually happens and all that, who knows, right? There's a lot of guessing game going on. It's not very scientific and things like that. Okay, but again, it's more a trend kind of picture that you need to think about. So now let's get to intro material about what makes this whole cloud and this and that exciting or providing opportunities for innovation and things like that. So if you look at this kind of a storage hierarchy picture, you start with things that operate at the nanoseconds or microseconds kind of way, right? When you are operating at the registers level, it's ultra fast. And then comes the cache memory that's in the same chip as the processor is. And then you have main memory. Even the cache, you can have L1, L2, and so on. Main memory, then flash disk, and then comes traditional disk, magnetic storage. Could even include things like optical storage. And then you could have tape storage. And then you have remote storage, right? It's across the network rather than being locally attached to the node. And so as you can tell, it's a pyramid because the width of any level is proportional to the storage capacity at that level. But if you go down, the speeds are lower and lower. The access time is lower and lower. And so it gives you an idea here. Traditional disk compared to CPU register level manipulation is 10 million times more time consuming. It's crazy. Jim Gray used to give an analogy. It's like he'll give an analogy about how close the disk head is to the disk platter where the data is stored in magnetic disk. It's like flying a 747 a micro inch above the ground or something like that. You have to be ultra careful, and that thing, in spite of all the shaking and all that, shouldn't actually hit the surface, the platter surface, because then it can cause damage. The head can get damaged as well as the data that's there can get damaged. So slower access, but at the same time, it's less expensive. So you have to decide, if you have a pot of money, how to divvy it up across these different levels. It's a non-trivial kind of optimization. There are links like this everywhere that you can go then find out much more about all this. So the remote storage is an important aspect of the cloud way of doing things, which is going beyond just a LAN environment to even a wide area network and such, right? So if you look at the storage hierarchy now, at the level of persistent store that's non-volatile. By the way, in this picture, we haven't even talked about non-volatile byte addressable memory. It's only referring to flash, but obviously all of that is sitting somewhere in this gap between main memory, DRAM memory versus SSD kind of storage. So it's not a very detailed picture, but it gives you a rough idea of what's going on. So you have Amazon EBS, which is block-oriented storage. There's a shared file storage. You operate at the block level versus at the file level versus object storage. The APIs are different for all of these things, and who's responsible for replication and all that is also different. This is also different from the idea of database managed storage, where in the good old days we used to effectively think of the disk as raw storage, and the DBM has completely dealt with the space management and all that, and we had more control over where what got placed and so on and so on. So the cost model of the query optimizer in those days took into account the size of the disk platter and the speed at which it rotates and what's the delay involved in going random seeks and so on, right? Which is different from directly addressable memory in the case of DRAM and so on, where there's no latency because things don't move and rotate and such. And so here again, the cost and the capacity and all that varies as you go along this. And there's also the business of encryption. In the cloud environment, especially, it's even more important than in an on-prem environment to make sure that when there are different kinds of people's workloads being done and these things are accessed through the internet and such, they're not behind the traditional kind of firewall and all that in an enterprise environment. They need to be much more conscious of protecting the data from random people coming in and trying to steal information and so on. So there's also the, like I said, the tape drive kind of storage. or even optical storage that might be used more for archival purposes or storing the backups and such. And here they are even talking about combining on-prem storage with cloud-based storage. So that's what this storage gateway is doing. This is on-prem stuff. This is the cloud stuff. So this is so-called hybrid cloud notion. IBM spent a lot of money, $34 billion, acquiring Red Hat, primarily because they support multiple clouds by giving an API that hides you the specifics of the underlying clouds it might operate on, Google Cloud versus AWS Cloud versus somebody else's cloud, Microsoft Azure Cloud and such. And that way, it gives you the independence to move your app from one kind of cloud to another cloud without the app having to change because you are using this API that Red Hat has defined, or combining stuff on-prem with stuff on the cloud, which is the hybrid cloud notion. So they talk about multi-cloud and hybrid cloud being the things that will last forever. No one cloud vendor's technology is going to take over the whole world, that you can forget the other cloud vendors. And so, so the kinds of reliability that are talked about are designated with 5 nines and 7 nines and 11 nines, which means 99 point and then 1 9 or 3 nines or whatever. So you count the number of nines you have, and that's accomplished by replicating the contents of these objects across multiple data centers, even across different geographies. So that's actually the next slide, but we'll come to that a little bit later. So I already mentioned the public cloud and the hybrid cloud. Then there's this notion of community cloud, where typically maybe a bunch of automobile companies will have a network that's dedicated to just for their usage. It's not open for anybody and everybody like a public cloud. And then you have the private cloud, which may be within a company, like even in IBM research guys established a private cloud so that every instance of IBM research in San Jose or New York or Zurich and so on need to have their own local storage and such, compute capacity and so on. So these are the types of cloud deployment. And then you have cloud service models, where you use the cloud resources in a bare bones way, and that's the infrastructure as a service, where you just use not raw storage per specifically, but virtualized storage, or you use compute capacity, or you use network bandwidth. The rest of the stuff that runs on it is your own thing, right? Or do you go one level up and have this notion of a platform as a service? It essentially provides operating system and application stack or a server storage network. Or you go one level up even more, which is software as a service, where DB2 or whatever might be running, and you pay for stuff as you use it in a metered way and all that, and you don't need to worry about installing it and all that. Whereas if you use platform as a service, middleware and all that, installation and use and even license fees might have to be paid by you, because you are using the cloud in a restricted way. They are not. So here are examples of some of these things. So at this level, it's only virtualized resource, and here are the examples of the different vendors EAS offering. The PaaS offering are things like this: Apache Stratos, Google App Engine, Microsoft Azure. You can use it in both ways, right? And then you have software as a service, where Microsoft Office is being made available on the cloud, and pay as you go model, or WebEx or Google Apps and things like that. Then there is this other one that's come up more recently, which is function as a service, where also known as serverless computing, where you deploy application code of a customer, as opposed to packaged packaged software like these things, right? These are produced by somebody else, which is made available to you for your use. Whereas here, you develop an app and then you dump it on the cloud. And the way you manage that is where a lot of flexibility comes, and we'll see more details about how this has implications on the database systems, leveraging this notion of serverless computing. So this also shows certain things with respect to how you deal with replication for disaster recovery kinds of reasons, and the current live data being replicated versus backup, the backed up versions of the data being replicated, right? There's even a notion of the logs being replicated. So at different levels, you may be doing backups and such, and you have to be careful about where these two different ones are. If you keep these two things close by, let's say in the San Francisco Bay Area, and then there is an earthquake, both of them might get affected by that earthquake, and then you are screwed because you lost the primary as well as the backup. But by having something far away in a different availability zone, you decrease the likelihood that both will get affected. By having, for instance, this guy in New York and this in California, you reduce the likelihood of both being simultaneously down and such. Sometimes these sorts of things are also done for load balancing reasons, right? So the more detailed discussion of all this is the idea of rack level protection and or things being co-located within a rack versus across different racks, but they are still relying on the same power and network capacity. But if you then go to the availability zone notion, then you will have different power domain and different network for these different guys. So even if the network is affected, it might affect availability zone 1, but not availability zone 2, things like that. If power goes away, this might be on a different grid than this one. The source of power is different for these things. And then you come to things like region and so on. This is where sometimes at this level, things like, oh, India doesn't want Indian citizens' information to be kept anywhere outside of the physical boundaries of India comes up. GDPR has a lot of those regulations, right? They might allow a German guy's information that's of personal nature to be stored, not just in Germany, but maybe it's okay if it's even in any other European Union country, but it cannot be outside the European Union. Those sorts of things are also big deal things. And this could even have implications on distributed databases and how they process requests for data that are stored in these different domains. Where can intermediate results be kept and things like that? So lots of stuff that I won't get into here, but you can imagine. So we had this gathering in December 2018, and the next one is coming up in 2013, where some self-appointed group of people, database people, sit together and scratch their heads and figure out where the field is, where it should be heading, and so on. I got involved for the first time only in this 2018 one, but this thing has been going on since, I think, 1988. So in August, a summary of the conclusions that we came to has been published as a CACM article. Earlier version of this also, which is, I think, what this link is. It came out as a research report, and some summary of it was also published in maybe the Sigmod record or whatever. So one of the subgroups that we all got divided into was focused on cloud data services. And two people at the time, Sailesh was in Amazon, and Fatma was in IBM Almaden. So they were the leaders of this group, and some of us took part in this group, and sometimes we also moved from one working group to another working group and all that. So these were some of the topics that were listed as the ones that need to be worried about, how to, in a careful way, combine data that belongs to different kinds of clients in the same system. what that means is subject to further clarification, whether same system means you are storing it in the same instance of the database system, or is it even in the same database within that database system, or is it even within the same table that you are mixing up different people's data? All of these things have various implications on the comfort level of these tenants. If they are competitors, they might be unhappy with their competitors' information and their own information being stored in the same table, because they might think that if there's a bug or whatever, some sleazy way in which they could get at their competitor could get at their information and things like that. It's also a question of, effective use of resources and such, whether it's the size, the memory that's dedicated to a buffer pool or some kind of storage capacity, or even CPU capacity and all that. So there are various implications of what it means to combine different clients, multiple tenants, information and computing and all that. Could there be bad interactions? If the same CPU is used for Wuxin's workload and my workload, could it be that my workload gets bad response time because this workload is gobbling up more of the CPU and things like that? There are all sorts of resource-oriented things. So this one is the one where the serverless notion means you don't have dedicated machines that are going to be, let's say, processing your queries. The data is spread on some devices, right? But where exactly your queries will get processed and which of the machines, multiple machines might be combined to do your query processing in a parallel fashion and so on, is not by pre-allocating such machines and other resources, but by dynamically, as needed, associating various compute resources that are out there for your query answering and such purposes. It could need not be just for querying, but it could also be for doing updates. So this is a very popular notion now. The idea being that you want to have better usage of whatever the resources are by adapting to the workload characteristics over time, overall improving everything, not just the usage of those resources, but also the manner in which you respond to the query or whatever, in terms of improving the response time and such, and reducing overall resource usage and such. So some of these things might be conflicting kinds of goals. If I want to give him a quick response time, the way to do that is to dedicate some resource and not let somebody else use it, because I don't know when his request might come. If I don't pre-allocate some resources, when his request comes, that resource may be busy, and so I can't immediately respond to him. So there are things like that which might mean that you have to think about all this very carefully. We've already talked about some of these sorts of things. How a traditional database system's architecture would have to be changed to make it go from operating in an on-prem environment to a cloud environment where the expectations are very different. As I said, at one point, you want to be able to do these things like auto-tuning and improve the usability of the traditional database systems, because you don't have any more of these well-informed, highly paid, or whatever smart-ass DBAs and system admins that you might have had in your own on-prem establishment. He's the VP for IT, right? So he has some such people sitting around that are helping him with doing the stuff that relates to POSTEC's IT requirements. But if POSTEC decides to go with one of these cloud vendors to deal with all the requirements, he then doesn't have to dedicate people in-house. And even the cloud vendor doesn't want to dedicate too many people, because they want to compete with other cloud vendors and reduce the cost of the services that they offer. And so they also don't want to be, having too many people that are highly paid people that are manually tweaking systems and such, or setting the right kind of knobs when installing a DBMS, or over time as things change, to adjust to changing workload characteristics, as well as the availability of hardware and software and storage capacity and networking capacity and so on. And the other thing is also the comment that was made was, while there was a lot of Hadoop and this and that kind of analytics oriented open source software, there wasn't a good distributed OLTP kind of DBMS out there that is based on open source. They also talked about how do you make the migration of applications that were running in the on-prem environment, where they might have run only on a single node, to now run on the cloud, also taking advantage of multiple machines and such on the cloud. And also having the flexibility of, as the workload changes, dynamically allocating resources or deallocating resources. And overall, have less of the machines that will be needed than the union of what these different workloads might have had at their disposal when they were in the on-prem environment. The idea is, with the cloud, by having a combined set of resources that can be dynamically allocated to various parties, you won't have the kind of low usage that happens in a typical on-prem environment, because the on-prem capacity will be made to be high enough that it can handle peak workloads. And at other times, when the workloads are not at their peak, then these resources are sitting in idle. Whereas in the cloud environment, they hope that across different users and their workloads, you can reallocate resources and such in such a way that things are pretty much at their maximum utilization. And that then means that the overall compute resources will be less than the union of the on-prem ones. You have to worry about, as I said, certain geographies demanding that their data not be allowed to go out of their geography, because they're worried that other countries' people might steal their information, and the other countries might not have the same kind of safeguards about personally identifiable information, PII, which the Western countries are a lot more sensitive about, right? Not revealing I have, I don't know, cancer or whatever. In some other countries, they might not be too bothered about it. They might easily share such information, but in the Western countries, they tend to be typically a lot more sensitive about this. They don't even like people necessarily being spied upon by having video cameras all over the place and all that, right? That's why these days, more and more, even cookies and all that, they ask for your permission as to what they can track and what they cannot track and so on. And also this business of, as the storage hierarchy that I showed you, as more levels get added to that, the implications of that. Okay, so I have to go faster, I think. How am I doing with time? There's no clock here. Oh, yeah. Okay. So you can read some of this, and I've already covered some of these things actually. State management for new ideas like serverless and function as a service and so on. People also want to make use of machine learning and other kinds of deep learning kind of ideas to eliminate database administrators, how to spread the data across devices, and how to repartition the data if there is skewed access to the data, and you are finding that a lot of people are going after the same shard, and so that machine or the storage that is keeping that is unable to handle it and things like that. Also, how do you run analytic workloads across data centers? In the good old days, you had the notion of a primary and then a backup, right? The backup came into play only when there were disasters like earthquake or whatever, or you wanted to roll in a new version of your software or application software or the DBMS software. And so during that time, the system has to be brought down. Then they would make the backup, the previous backup become the primary and then reroute the workload to that one. And then once the first machine gets upgraded to the new hardware or software, middleware or operating system, whatever it is, then they'll re-establish that as the primary. There are things like that that you have to worry about. You also have to worry about when it's beneficial to move to the cloud and things like that. There are situations where people have noticed that, the cloud vendors are also trying to maximize their revenue, right? So it's possible that if you are going to use some cloud for a long enough time, you might in the end wind up paying more. But the difference that people talk about is with an on-prem environment, the capital expenses are very high because upfront you have to buy the machine and everything else, software license, this, that. Whereas in the cloud environment, it's the operating expense that is being spread across. It's effectively like taking the capital expense that would have been spent upfront and spreading it across a long period of time because you are paying as you use the cloud resources. So sometimes people don't mind ultimately winding up paying more than if they had invested in their own on-prem stuff upfront. Because it's easier to pay smaller amounts than upfront having to pay a large amount. And then there is all this notion of disaggregated storage that we'll get into, and including non-volatile random access memory and things like that. So these are some of the systems. I won't necessarily talk about every one of them. Ultimately, I would like to do that, but again, you'll see some details that I'm going to show. So what is this whole business of storage disaggregation and such things? In the traditional way of doing business, notice the thickness of this arrow. That means that the bandwidth is very high. It's locally attached storage to a node. This is the CPU and this is the storage that's attached in a high bandwidth way. And everything happens here. SQL to transactions to caching to logging and so on. And the storage is, to some extent, the way I said, it's used like a raw device. But when you decouple storage from compute, you might first make it go across a network or whatever. And as a result, the bandwidth is lower. LAN versus WAN, it'll even be more of a difference. And exactly what assumption you make about this is now a function of whether you still treat it like a raw device or you are relying on a file system here or an object storage system here and so on. Whether you rely on the, access it at a page level, even though it's still virtualized, you still have the notion of page versus you only talk in terms of files and API calls that are at the file level. That's what that object thing was. That's one thing. And then you might begin to do state separation, where you might say the top part is memory less in a long-term sense. It's going to bring the data that the query is going to be post against, and then the data gets discarded. But even if you're doing updates and deletes and so on, momentarily the data gets brought from the storage node to this compute node. You make the changes and then you write back the changes. Exactly how you do that, we'll discuss. Whether you write back the pages themselves or you produce log records and then you send the log records to the storage node for it to separately apply those changes to the database pages than what was done originally by the compute node. So depending on where you do the drawing of this line, different things will happen on the compute node side versus the storage node side. So this is called stateful compute versus stateless compute, because here you are still worrying about longer term kinds of things that the compute node is dealing with. Whereas here it's just not a permanent cache, but a volatile temporary cache to improve performance that you keep some stuff here. So Aurora serverless, they have been, I would say, more of a pioneer in this kind of space. So they talk about database storage, scalable database capacity, request routers. So it's a question of when an application wants to access some data for read or write, exactly how does it find its way around the network or the cloud to locate a place from which this query will be processed, all the usual stuff, right? Parsing it and doing query optimization and all that stuff gets done. And how do you do this in a way where, in spite of failures, this request will still get satisfied? If the node to which you sent it originally goes down or it's not performing fast enough, the expected processing, you might now reroute the query to another node, things like that, right? And also whether you pre-dedicate resources or you dynamically bring up these compute resources. The problem with compute resources being dynamically allocated is that you have to then effectively install the software. Even if it's installed, you have to start it, the database code on the compute node side, right? So that might take a while. And so that might not be acceptable from a response time viewpoint. That's why there's this notion of warm pool of instances that are kept that they can dynamically allocate for a particular request to process. So go read all these things, and these guys got the award and all that, right? So there's more details about all this. So one of the things that they decided to address in the Aurora project was to help customers who are using MySQL in an on-prem way, applications that are already written and so on, how to enable such apps to be moved to the cloud without any hard work having to be done by the application writers. So what they did was to keep the API the same, but they changed, if you like, the inside of MySQL to take advantage of all the whiz-bang stuff that they have in their network, in their cloud. And so that project, when it succeeded, so it now brings with it all the benefits of stuff being done on multiple machines and dynamically allocating resources and deallocating resources and providing high availability and all that via replication and so on. So there's a lot more detail about all this that I unfortunately cannot get into now, but some of the slides that I hope to show will show that. But they still have this restriction that the so-called head node is the node from which, or the master node is the one from which updates can be performed. These replicas that are there are only read-only. Because if you begin to allow multiple nodes to be able to even modify the same piece of data, that goes to the shared disk architecture that I had worked on the IBM mainframe, which is the opposite of shared nothing architecture. And Oracle, of course, is the Oracle RAC does that, and there were other companies that did that before. These guys are trying to stay away from dealing with the complications of when you allow multiple nodes to update the same piece of data, you have to do locking across machines, global locking, cache coherency, because a page might have been changed here and then somebody here wants to change the same page. And now you have to make sure he gets hold of that latest version of that page and does his thing. And just releasing the data lock won't help, because the data locks being released means that he can get the data lock on this thing that he just modified, but you have to now make sure that he sees the latest version of the page. And so this is all similar in flavor to cache coherency that the computer architecture people are worried about in a multi-processor environment where individual processors have their own caches, but they also have like L1, which is not shared, whereas L2, which is shared, and things like that. So there's a lot more detail about this. My keynote at that workshop attached to ICD had to do with my argument that the people like Dave DeWitt and Jim Gray, who passionately talked about why shared nothing is good, when some of us were not agreeing with them, those sorts of people, Jim is of course not around, but Dave DeWitt and Mike Stonebreaker and such are now in the cloud environment effectively saying shared this is what it is, and we need to now make things work. But still, in a product sense, people are for the time being, taking the shortcut of saying for any given piece of data, any shard or whatever, only one node can update it. But across different shards, the master node can be different, but for given shard will be one. But some half-assed stuff also has been done in this space. And also because the bandwidth requirements are different and they want to optimize the network usage, as I've been saying, instead of sending the log records, instead of sending the modified pages from the compute node to the storage node, they only send the log records written by the compute node. And so by doing that, they've shown in their paper how this reduces overall the number of persistent storage writes and also the usage of the network compared to a different approach that had been taken in other environments or even for MySQL as a way of providing high availability, where they would send full page images from the originally updating node to the backup nodes. There are a lot more details that you can find in the papers that I have linked to with this. They also decided that dragging all the data from the storage nodes up to the compute nodes and then processing them for queries, especially queries that are touching a lot of data, is not the best thing to do, because in this direction, it's still pages that are being brought up. So then they said, okay, it's better to, just like in Spark, for instance, for remote sources, you can push down predicates, including even joins. If the remote source has table 1 and table 2, and you're doing a join of table 1 and table 2, might as well push the join. I talked about all this in the query processing talk that I gave in Osaka. They push down the predicates themselves. And so these guys, the storage nodes themselves, do some level of processing. And this is where they have to now know how to interpret the contents of those pages. And they were anyway doing this because to apply the log record changes when they are receiving log records, they need to know the format and how, they need to have the metadata to be able to interpret the contents of the pages. It's not like they're just dumb page servers. They're actually aware of the contents and such, and formats of records, data records, and so on. So this is in some ways similar to what was done eons ago in the context of database machines. Decades ago, it's been done. But also Oracle did it in their, I'm forgetting the name of this system, where they separated this even in the on-prem environment, where they would push down to the storage nodes, this kind of predicate evaluation. They introduced this idea that just two nodes can simultaneously have the ability to update the same piece of data. But it was done in a very ad hoc way. Between nodes, they do page level locking, but within the node, they do record level locking. This is age-old technology, at least in the IBM world, because even pre-relational system like IMS did this forever. And the thing that some of us did was to then go from two-way sharing, as we called it, to n-way sharing. Any n number of machines could be having equivalent access for read and write and so on. So there's more stuff here that has to do with, now even a data warehouse that's on the cloud, that's Redshift. Aurora was more for OLTP. And there are some exciting things that they've done more recently in this space to make it even, give you the ability to do ML kind of work in this parallel environment. This is something like, instead of running the ML models outside and sucking data out of the database and feeding it, why not like a user-defined function and such things run the ML logic itself within the database, thereby reducing the amount of stuff that you need to bring up and so on. Microsoft has been also very active in this space. They, in some ways, have done work that's similar to Aurora, but they also done a few other things that are different. A lot of these guys work in a way where they try to combine both the OLTP workload and the analytics workload and take advantage of multi-versioning of the database changes to have something like snapshot isolation, reduce the impact of concurrent read and write to the same piece of data by making the reads do look out reads read a slightly older version of the same piece of data for which there is more recent update that might not be committed, and hence if you go to the most recent data you would be forced to wait and things like that. And they also said if a primary node or secondary node goes down and comes back up, it'll take a long time before the buffer pool of that node will get populated. And so any requests that go to them will take a long time to be able to satisfy it. So they said it's an optional feature for even the contents of the buffer pool here to be periodically stored locally on persistent store. So when you come back after a failure, you can reload that. Of course, in the meantime, some of that data could have changed. So you have to make sure that, you know, if there is a more recent version sitting somewhere else, that you invalidate this old version that was sitting on persistent store that you reloaded and such. I won't get into, you know, further discussion about these things. Effectively, I've summarized for you what has been done by Microsoft. And then the particular project called Polaris, a system called Polaris, was to make distributed SQL work in what used to be called Azure Synapse. And this is essentially parallel processing and so on. They are also in this way trying to converge the traditional data warehouse that might have operated against structured data with the data lake, which is this, you know, dump all the world's data there in whatever form it was originally produced, weird file formats and data structures and so on. And there is now this notion that I discussed in the talk I gave in Osaka, where they're trying to, on top of a data lake, something called lake house, which is a way of leaving the data in place in the data lake, and instead of having to drag it all the way to a traditional DBMS and then being able to do fancy query processing there, try to even give a structured view of this semi-structured or unstructured data in a data lake through this concept of lake house. And so people like the Databricks guys have also done some work, and I talked about a query optimizer that they developed for that context. Okay, so Google has got a number of systems, and so there are more details here. It looks like I have to stop now, right? Yes. So they have relational systems, non-relational systems, and also in memory. These are obviously not in memory, and they've developed a newer system. But this is an old one, which was developed eons ago, long before public clouds became a big deal. Internally, they had a worldwide way of managing their own. It's like a private cloud, right? And it's high performance and all that, and fancy, fancy way of replicating the data. They make use of atomic clocks and GPS to do the ordering of events and so on and so on. So it's a system that until the Google Cloud came into existence had been used internally for Google's own applications, like whether it's search or Gmail or YouTube and on. There are many things that they have for which the workloads are incredibly demanding, both from a performance viewpoint and capacity viewpoint and all that. And so they've provided high levels of reliability and such. And in that context, this has been written up about a long time ago, so I won't dwell on this. Initially, it was more like a key value store, and then they added the capability of SQL through something called F1. And even at the SQL level, they did some fancy things like even having a hierarchy of tables, somewhat like object relational. They even allowed for sub-record concurrency, finer than record level locking, and so on and so on. There's this notion of clustered hierarchical tables and such things. And they passionately argued in favor of synchronous replication, even across the globe with 5 replicas, which might elongate the response time, but they felt that's still worth it compared to the headaches caused by eventual consistency, as was the norm in many systems then, as well as even now with some of these NoSQL systems. Because if you do have conflicting updates happening, eventual consistency causes conceptual problems, and fixing them requires a lot of manual effort, and it's not always obvious how to fix it. So they felt that even for the smartest people within Google internal usage, they are very bright people and highly paid and all that. They still thought that that wasn't a good compromise to make. So you can imagine now if Joe Blow kind of people have to deal with these negative implications of eventual consistency, it's just not going to be the same, meaning it's not an acceptable thing. So they, as a result, to go for synchronous replication. So then the new thing that's been done is this system called AlloyDB, which got announced only in April or so. It's similar in flavor to what Amazon did, where Amazon first made moving MySQL apps to the cloud simple with the same API and so on. Then they did it for PostgreSQL, whereas these guys from day one decided to address the same kind of capability, but for PostgreSQL. They have not done anything with MySQL. And on top of the sorts of things that Aurora did, these guys also decided to expand the scope by not only dealing with row store way of storing the data, but even optionally letting columnar versions of those tables, even subset of the columns, to be maintained so that queries can dynamically be routed to using the columnar version than the row version if the consistency requirements are okay and so on. And in so doing, they can even do it. They even allow for automated ways of determining which columns are the ones that are worthy of being replicated in a columnar way by making use of AI technologies and machine learning and all that, by analyzing the workload and such things. So they also allowed for this concept of bringing into the DBMS the handling of machine learning models, feeding them with new data and looking at what comes out and things like that. So that's called Vertex AI, which is AutoML and AI platform, the combination. And so the predictions based on those models can be done inside of the DBMS, and you can combine more easily and also more efficiently the information inside the DBMS. So I won't get into this, but there's a lot of similarity. This business of sending log records to the storage server for it to apply the changes and so on are in many ways similar. So this is why I was telling you that there's a lot of similarity between this and what you, in a different context, have done. So they also even allow simultaneously making use of the row version of the data as well as the column version, things like that for a single query. CockroachDB is a startup that's working on OLTP in a distributed context with some fancier features. They're all, like PostgreSQL is very popular as a thing that they should support. And some of these guys will allow read-only queries to be run on the read replicas with certain relaxed semantics than running it on the head node or the primary node, where updated versions might be maintained in a most recent fashion and such. So look at this. They have this notion of follower read, which is not exactly the same as snapshot isolation. They are even supporting spatial data types and things like that. Some of these sorts of systems are built on top of row stores, of key value stores produced by others. So in this case, they did it on RocksDB. Okay, so not all the people necessarily build all the data manager layer of the software. They rely on some other thing, but they provide some fancier features on top. So Snowflake, okay, yet another company that's gone public and made a lot of money and so on. Cockroach hasn't gone public, whereas this one made a ton of money after long time's existence. Sort of in even a non-cloud environment, they were doing the warehousing stuff. And these guys provide you a huge workload where 70 million anonymized queries they made available for other people to play with and so on. Alibaba has lots of stuff. Look at this OLTP, OLAP, NoSQL, similar in flavor to what I was showing earlier about Google itself on its cloud supports their homegrown database systems, both relational kind and document database and so on, as well as this more recent thing called LIDB, and also running somebody else's code, Oracle running on the Google Cloud or PostgreSQL built by the original people being run as is on it and so on. So they've got something called PolarDB, and they, worry about these sorts of things, compatibility to MySQL, PostgreSQL. They keep 3 copies rather than the 5 copies of Spanner. They are pushing down to the storage level, even table scans, right? And you could even push into the drive itself by manipulating some of the sort of what we used to call channel programs in the IBM world. They can even, this is like in the database machine world, they used to talk about making the read-write head itself do some filtering and so on. This could also happen because you could use FPGAs and such at that level. You see FPGA, GPU and such. So it all gets complicated as to who does the address mapping, because with flash memory, you don't do in-place update. You always have to write it to a different place, which is very different from the way magnetic storage worked, right? So that causes a lot of garbage collection and all that to be done. And somebody has to keep track of, for page 1 of this file, what is the current location? So there's a notion of a logical page 1, and then there is the physical location where that is. And over time, that physical location, somewhat like shadow paging that was done originally in System. Okay, so they are talking about even employing parallelism during the scans and skipping and so on. This synopsis and such things can be used. Statistics that are kept of high key, low key, or even more details can be used to skip some partitions from having to be scanned if you don't have indexes, for instance. These are like approximate indexes. Okay, there's no limit to all this. They even want to take advantage of RDMA by doing remote memory access from one machine to the memory attached to another machine and things like that. Some of this you have to be careful with the security aspects of this, right? So they are combining shared storage and shared nothing concepts, and that's the end. Or any such thing, but I just wanted to present this whole variety and make you go read these things on your own and find out much more. But overall, it's a very hot topic. Whichever company you look at, whether it's in the West or the East and so on, and lots of research work being done. There are people like Joe Hellerstein working on 2 steps forward, 2 steps back, and so things like that. But there is another talk I'm going to be giving, which will give overall view of the database area. I'm going to give it multiple times next week in Hong Kong. So I welcome you guys to keep tabs on, again, I've listed some of that in my spreadsheet. I'm going to give like 6 talks in 6 days in Hong Kong. Some talks will be repeated and so on. So there is the notion of even within the operating system, trying to introduce relational concepts and making the operating system itself make use of tables and persistent storage and such. This is not as revolutionary as it sounds. DBOS, this is the project that Sam Madden and Mike Stonebreaker and a bunch of others are working on. It turns out in the IBM world, eons ago, something like that was done. But it wasn't a full-blown relational notion in the hardware. They had locking and latching at the horizontal microcode level, and then they had indexing in the vertical microcode level. But they didn't have SQL at that point. Later on, SQL got built on top. But the operating system itself made use of these relational constructs like table and such, records and so on, in its metadata management, whatever it is doing, right? Whatever persistent data it's keeping. These guys are now worked on taking it to the next level and making use of even AI-ish kind of concepts inside the DBM, inside the operating system. Instead of that thing doing its own thing, which is got overlapping functionality. Any questions, comments?
So I have one question, the general question. Nowadays, this rest of things, RAFT.
Raft, yeah.
So do you have any comments on the raft and the typical community?
I haven't spent enough time to dig into that. You see, there are lots of these sort of leader-based protocols for determining at any given time how to handle two-phase commit kind of notions, how to provide atomicity across nodes. They are all trying to do this in a way that goes far beyond what I did in my work just about 40 plus years ago, which was the presumed commit. They are also to some extent in this kind of situation trying to deal with replication and this whole quorum idea and so on. See, in our case, we didn't have replication support in our star. We had the notion of snapshot, which is like materialized view, right? And that was handled in a very special way. It wasn't necessarily synchronously maintained snapshot. And so we also didn't worry as much about Byzantine behavior and such things. We assume that the nodes are well behaving, that they won't lie and so on. So, and also, even though we were dealing with a geographically distributed environment, we didn't spend as much time on really, really high availability and such. So some of these guys, especially in the context of blockchain, this has become even more fashionable, whether you have this leader notion or not, and are the nodes known ahead of time. So these leadership-based things assume that it's more like a permission blockchain system. Not only do you know who the participants are, but you know exactly how many are there at any given time. Because if you're doing voting and all that, you need to know how many people are there. Otherwise, it doesn't make sense to talk about if majority of the nodes that are there agree on something, then we'll go ahead and comment and expect that. But I haven't done a detailed look at all the variations that are being developed in that space. You are showing your hand because time is up. What? Oh, to go somewhere? Oh, I see. Okay. Yeah.
Maybe last question.
Okay.
In the slide you showed in the 2000, you showed some features like data sovereignty or something.
Yeah.
It's like a feature that you want to add in the databases, cloud databases. So if you have a new feature, a whole new feature that you want to add in the running data cloud system, and are there sometimes situations that you need to really just from ground you have to code implement a new data cloud or
yeah, I mean there will be such things. So the So the trade-off with this business of on-prem versus the cloud is also, I didn't even mention that. In the case of on-prem, you have longer release cycles and you go through as a customer in business of having to make the decision when to switch from the current release that you are using to some other release, subsequent release. It might not necessarily be the, if you had 1.3, you are not necessarily going to go to 1.4, you might go to 1.5 and things like that. So from the perspective of the producers of such software, it's also the case that they have to think about all this, how easy it is for the customers to migrate, how long does it take to install the new version and so on. Whereas in the cloud, it's like all the apps we all deal with in the phone, right? You don't even know when it's going from one version to the next version. A lot of times, if you have set it up like that, it'll automatically update to the new version, right? And so, but in both cases, if you're not the producer of the DBMS, you're merely the user, you don't really get to dictate and demand and get immediately some functionality, right? These organizations listen to their customers, but they then have their own processes to determine when to introduce some feature. For instance, IBM took forever to introduce certain concepts like sequence numbers that Oracle introduced early on. Things like snapshot isolation, keeping multiple versions of a piece of data, we took forever to do because we thought something else was more important, right? This shared disk architecture thing was considered to be more important because it provides a lot more flexibility with respect to dealing with failures, improving availability, and various other things. Rolling a new update, meaning a new version of a system across the nodes of the cluster in a way where you don't have to bring down the system to introduce the next release of the DBMS. So, but you as the poor end user won't be able to go unless it's an open source system and just because it's open source, that doesn't mean you have the skill to mess around with it, right? So if everything is in the right, if all the stars have aligned properly, maybe you can then go change that system to introduce the functionality that it's lacking and so on. This is where my comment the other day, where did I give this comment? Oh, that was probably the talk originally in Osaka. I make this comment about let 1,000 flowers bloom. That's become common. It's not a good idea because everybody, when they think of something and if they notice that the existing system doesn't provide that functionality, then they go off the deep end by writing yet another DBMS with its own weirdo API and so on, instead of picking up one of those existing systems which is closest to what you want and adding the thing that it doesn't have. But of course, that requires a lot of hard work because you have to dig into that damn thing. And depending on how badly or well it was documented by the people who produced that thing, it might not be that easy. But then you also do the bad thing because when you write this new thing, you're not only creating this yet another thing, it might not be usable with the tools that were already around. It has its own ways of doing certain things which are incompatible with something else. So for somebody to make use of this thing, they have to have a brain transplant and all that, right? So you also do a bad job of documenting this thing because this becomes like a cultural thing, right? Because you say, what the heck, nobody else might take the time to